My name is Tarian Gruber. I'm from the University of Alabama. My mentor out here is Dr. Nikolai Kukutareva, and this is my second bi-weekly research report. I'm reporting on pump probe laser illumination of oil and water samples. Basically, what we're doing is taking a high-intensity laser, we chose green, and illuminating oil droplets in water. Due to the photophoretic effect, these droplets begin to change form and disperse. We observed and monitored the kinetics of oil film aging by analyzing the time-dependent holographic fringe pattern image. And that's created by a low-intensity, we chose red laser beam, and that's where the pump probe title comes from. We use the green beam as the pump beam and the red beam as the probe beam. Right now, the most common method of dispersing oil is the use of chemical dispersants. The two main components of chemical dispersants are a surfactant and a solvent. Surfactant molecules are made up of two parts, an oleophilic part and a hydrophilic part. The oleophilic part is attracted to the oil and the hydrophilic part is attracted to the water. The solvent transports and distributes the surfactants through the top of the oil slick. The solvent basically penetrates the oil slicks and delivers the surfactants to the oil-water interface. And at the oil-water interface, the oleophilic part arranges itself towards the oil, the hydrophilic part towards the water, and this reduces the surface tension in the oil slick and causes the oil to basically break up into the water column. It was a lot of opinions both for and against the use of chemical dispersants in the Gulf of Mexico oil spill, because with everything, there's some pros and some cons. But chemical dispersants are capable of rapidly removing large amounts of certain oil types from the sea surface by transferring it into the water column. They delay the formation of persistent water and oil emulsion, and they typically can be used when all other at-sea techniques are hindered by weather and other resources. They have other methods for dispersing oil like filtration and other things, but sometimes those can be expensive, and chemical dispersants is the best way to go about it at this time. But they do have some drawbacks. They have little effect on very viscous floating oils. When the oil is very viscous, the solvent doesn't really have the power to penetrate the oil slick, and usually the chemical dispersant runs off into the water before the solvent penetrates and delivers the surfactants. Everybody knows that chemical dispersants have certain levels of toxins. The levels of toxins in the dispersant has decreased over time, but there are still small numbers of toxins within the dispersants. When you're out in deep ocean, the toxins aren't as concentrated because of the mixing of and the turbulence of all of the water. But close to the shore, where there's not all that mixing and that turbulence, then the toxins can continue to have a high concentration for a long time and damage marine life. The use of lasers as oil dispersants is a relatively new concept, and not much has been written about it. It is possible because of the photophoretic effect, which explains why small particles suspended in gas or liquids migrate when illuminated by a sufficiently intense beam of light. This is owed to a non-uniform temperature distribution of the illuminated particles. In laser photophoresis, particles migrate once they have a refractive index different from their surrounding medium. The particles with higher refractive indexes than the surrounding medium move away due to radiation pressure. And radiation pressure is basically just the energy density of the lasers that we use, and the energy density can be compound or found by just taking the intensity and dividing by the speed of light. Optical dispersants offer many potential benefits, and that's basically why we're doing the research. They may be used remotely, whereas you've seen in my other slides, the chemical dispersants have to be used by large, gigantic planes or big boats with a lot of people, and optical dispersants can be used from a control room. They're localized, so we can target specific oil spots, and we can even penetrate deep into the water with higher intensity lasers, where chemical dispersants usually break the oil up from the surface, but as it gets emulsified and the viscosity increases, the power of the chemical dispersant wears off, where you can't really wear off the power of a laser. We can clean vertical structures with these lasers. Like I said before, we can go deep into the water and penetrate. And they're already currently using lasers to understand and monitor the breakup of oil film so they can understand the efficiency of chemical dispersants. The same lasers that they use to understand the efficiency of chemical dispersants can actually do the dispersing. So you can actually cut a step out of that. This is basically my lab setup. This is a hydraulic table. It stays level no matter how much pressure you put on it. And these are my lasers. This is my red laser. It's a low intensity laser. And this is my green laser. I was told that it was a very important laser. It came from Germany. He gave it a name and everything. These are my mirrors. Basically how I reflect my laser light. And that's my detector screen that I use for my holographic images. And this right here is a better schematic of what's actually going on. I know that was kind of confusing. But what I basically do is just take this red laser. This lens right here expands my red laser, as you can see right here. And this laser is reflected onto the oil sample and hits my detector screen where it produces the interference fringes. The green laser beam isn't expanded. It remains localized, so we can basically maintain the intensity. And we have another detector screen to understand those images. This is my oil and water sample. It was illuminated by a continuous 532 nanometer wavelength green laser light. This right here, we use monochromatic laser light, and for some reason we don't understand why we produce these yellow colors when we took the images. We don't know if it's because of the cameras we used or the optical components of some of the other things, but we shouldn't have any yellow coloring because it's only red and green light. But also this image shows, I don't know if you can really see, but it's a very, very thin film on the top of this water sample. And that thin film was produced by a long exposure to green laser light. We heated our sample and we stirred our sample, and we were not able to produce that film. All right, this is a dynamic hologram of the large oil droplets and the thin dispersed film. Like I said before, my green laser light beam wasn't expanded, so you can see it has a high intensity and localization. Here, even when reflected off of the surface, and the screen was approximately 70 centimeters from the surface of the oil and water sample. The duration between this image capture is about 4 seconds. So this hologram was actually moving very, very rapidly, kind of violently. This image shows the kinetics of oil film aging seen in probe red beam duration illumination by the pump beam laser. These photos were taken from the images projected on the white diffuse scattering screen that was in my picture, and that was approximately 4 meters away. And that's how I got to such good resolution here. The duration between capture of this image, though, is about 30 seconds between each picture. And the red laser beam was expanded so that I could basically get better holographic images. And as you see right here, what this image basically shows is this is the oil droplet that we're illuminating, a hologram of it. And these are the interference patterns that it produces. And as you can see, as time goes on, right now it looks like 3 oil droplets merged together to create an island. As time goes on, a 4th droplet begins to emerge, and the radius of it increases. And if I continued on, eventually this whole island would break apart. So in conclusion, the pump probe beam scheme allows us to observe kinetics of oil film aging during laser illumination, performing the same illumination experiment, but substituting the oil and water sample with the geranium broth yielded very different behavior. With the geranium broth, it was organic. We didn't see any significant interference patterns, and with this hologram right here, this image was taken every 4 seconds, and you can see how it moved around. We didn't get any motion in the geranium broth solution. So this actually could result in a way of discerning between organic compounds and oil and water.